you. Okay, inverses. The main thing you need to remember with inverses, or did you do inverses in Algebra 1?
Maybe they weren't called that.
If you did, they weren't called that. That's fair. The main thing for inverses is switch x and y. Yes, it is a reflection. So maybe the main thing to remember with inverses is switch x and y. There's 3 things we'll do with it. 2 of them are switch x and y. So first let's find an inverse of a set of points. And how we'll do that is switch x and y. So let's say our set of points are 2, 3, -1, 4, and 4, 2. And you put them in the fancy brackets to kind of indicate that this is a set of points. I guess I should have given the instructions would be find the inverse of the relation. So, relation is like a more generic term for functions. Like if I don't want to specify that it's a function, I'll just say find the inverse of the relation. So its inverse then, again, switch x and y. This does not mean you change signs. It doesn't mean change the signs of x and y. It means switch x and y. So instead of 2, 3, we'll have 3, 2. And instead of -1, 4, 4, -1. And instead of 4, 2, 2, 4. The hardest part is drawing the bracket. Probably true. So, switch x and y. Probably don't need another example of that. Just switch x and y. Again, the thing people get confused of, they hear switch, and I think their brain thinks, oh, switch the sign, because that's, I guess, usually what we switch. But don't change the signs, just trade the x and y, make them trade places. Alright, Roman numeral 2. For equations, get this, we do something completely different. We're going to switch x and y. Okay, now, I mean, it's simple to say, but the practice is a little bit harder in the equations than the points. It'd be hard to be easier. Let's find the inverse of f of x. So we'll start with a function. And then use inverse notation if possible. Okay, well, we may not even know what inverse notation is yet, so we'll get there in a minute. Find the inverse of f of x, meaning switch x and y. Use inverse notation if possible. So let's start with f of x equals 2x minus 4 over 6. And I'm supposed to switch x and y, except that there's not a y. Right? Or sort of, there's a y. Well, f of x is the same thing as y. So let's make that little swap. And then, in place of y goes x, and in place of x goes y. And that is our inverse, but we don't like that as an answer. Because what do we usually like to do with equations? Solve.
Or simplify.
Or simplify, but solve, finish that statement. Solve for what?
Solve for x, right?
Well, it's already solved for x, so let's solve for y. So what we didn't say, and what's not usually said, but needs to be sort of understood, is after you make the switch, solve for y, and then we'll see about inverse notation. Okay, so let's multiply by 6. I like that. Yeah, then we're almost there. Let's add 4 to both sides. Divide by 2. So y equals 3x plus 2.
3?
Yeah?
Okay, yeah, I see.
Divide by 2? 6 divided by 2? Still 3. So that's my inverse that's now been solved for y. You can maybe start to see where partial credit can be had. I will give you some partial credit if all you do is switch the x and the y. I mean, that's super easy, but that at least shows you have an understanding of the inverse. Then you get some more points for solving for y. And then, is this a function? Y equals 3x plus 2?
Yeah.
Just think about what it looks like. Right, up to slope of 3. Yeah, that's a function. So here's function notation. F with a little negative 1. That's inverse notation. That means the inverse of f is 3x plus 2. What's that? It was definitely longer. The concept was just as simple, right? Switch the x and the y. The longer part was solving for y. Well, let's try another one of those, because sometimes weird things can happen. Let's go with f of x equals x squared minus 7. So that means y equals x squared minus 7. After you do a few of these, most of you won't show that step because you'll know that f of x is y, and then you switch x and y. So in place of y goes x. In place of x goes y. Everything else stays the same. So that's now y squared minus 7. So that is the inverse. But I'm not done yet because we have to solve for y. So, what would you like to do to solve for y? Add the 7. And then, what would you do to get y by itself? I like that. Kind of. When you take the square root of both sides? No.
Could you divide by 9?
What if I had x squared equals 9? A little off to the side here. What does x equal if x squared equals 9? 3 isn't wrong, but it's not complete. It's plus or minus 3.
Where did you get 3 from?
This is a separate problem over here. To remind us that when we square root both sides,
Oh, plus or minus.
you've got to put the plus or minus on there.
Why?
Because if your answer is 9, you could have squared 3 or you could have squared negative 3. When you put the square roots on, you've got to put the plus or minus on. So that's where that plus or minus comes from. Okay, so that's pretty much my answer. But that last statement said, use inverse notation if possible. Is this a function?
Probably not.
Why not?
Because possible answers.
Because there's 2 possible answers. That's a good answer.
By the tone of voice.
By the tone of my voice, that's another good answer. If I plug in anything for x, like whatever I get here, there's going to be 2 outputs, the positive one and the negative one. So that's definitely not a function. So it's still the inverse, but I don't get to use the inverse notation because it's not a function. So it's not eligible for fancy notation. Let's back up a minute here. X squared minus 7. What's the graph of that look like?
Parabola.
Parabola. Has even been, wait, how has it been adjusted? Down 7. And my picture here doesn't need to be perfect for what we're going to do. But a parabola down 7. No, but I want to illustrate about this function stuff. What's the vertical line test tell us?
It is a function right there.
It is a function. But the horizontal line test, it fails. And if it fails the horizontal line test, that tells us that the inverse is not a function. It's the x, y, y, x stuff. For every x there's one y, for every y there's one x. Doesn't pass the horizontal line test, the inverse is not a function. Be careful, it still has an inverse, but with that plus or minus thing, it's not a function. So you can tell from the equation if it's not a function, but you can also tell from the picture if it's not a function. So you don't really need to do both, but if you're confused, one is sometimes easier to think about than the other. Again, so this is my answer. I just can't write f inverse because it's not a function. It's an inverse, but it's not a function. Roman numeral 3, and final. Checking inverses. This is not a switch x and y thing. So the first two things, just switch x and y. If it's points, you're done. If it's equation, well, you got to solve for y. But checking inverses, here's where we get to use the Fogg and Goff thing. If Fogg of x equals x, and g of f of x equals x, then f of x and g of x are inverses. And so you have to check, when I ask you to check, you have to do both and show that they're both equal to x, f of g and g of f. So those problems always have two pieces to them. Well, potentially two pieces. If f of g of x is not equal to x, you can stop there and say they're not inverses. But to show that they're inverses, you'd have to do both. So let's say f of x equals 1/2 x plus 5, and g of x equals 2x minus 10. And the question is, are they inverses? And sometimes you can maybe tell by looking, because like one of them multiplies by 1/2 and the other multiplies by 2. Those seem opposite. One adds, one subtracts, but a 5 and a 10, I think we should check. So f of g of x means f of 2x minus 10. I'm going to have to do both, so the order doesn't really matter. F of g of x. So now I'm going to grab my f function, but instead of plugging in x, I'm going to plug in 2x minus 10. Let's see, that's pretty easy. Like if it works, it's pretty easy, right? Because that's x minus 5 plus 5. So that's a yes. But I'm not done yet. I have to check the other way around. G of f of x. So g of 1/2 x plus 5. So grab the g function, but instead of plugging in x, I'm going to plug in 1/2 x plus 5. And
10.
And once again, let's see, that would be x plus 10 minus 10. That equals x. So yes, f and g are inverses. And I guess depending on how the question is worded, make sure you answer the question. Yeah, the book specifies clearly. Determine whether each pair of functions are inverse functions. Write yes or no. I like that it specifies, because so many times students do all the work, and they're like, yeah, look at all that. And I'm like, yeah, well, you didn't answer the question, so I can't quite give you full credit, even though you clearly knew what was going on. So if it says, are they inverses, then make sure you answer yes or no. Another example of that, or are you okay with f of g and g of f? Alright, so page 397, 11, 13, 15, 17, 19, 31, 33, 35. And 15, 17, and 19 you don't have to graph. It asks you to graph them like the function and its inverse, but you don't have to do that. So the first two are points problems, the second three are equation problems, and the final three are checking to see if they are inverses. So 15 minutes, 8 problems. 2 minutes per problem, although the point problems will take far less than 2 minutes per problem. Oh, and before I stop recording, and while you're still looking, this was also due Wednesday. So 3 things due Wednesday. Page 389, worksheet 6.1, and page 397.